Hello, welcome back. In this video, we'll discuss graphing rational functions using limits, intercepts, and end behavior. And in particular, we've got this function. So our goal is just to find all of these quantities, or I guess mathematical objects, x-intercepts and y-intercepts, any holes in the graph, vertical asymptotes and horizontal asymptotes. And then for these last three, we're going to find the related limits, because we know that vertical asymptotes, horizontal asymptotes, and holes are related to the limits of the function. And then we're going to use all of that to graph the function in the xy plane. So to start, let's talk about the x and y intercepts. And the x-intercepts are just where the graph crosses the x-axis. Let's see the graph of that. And the y-intercept is where the graph crosses the y-axis. Now with the y-intercept, we're only going to have one, and because it's a function, but we might have more than one x value where f crosses the x-axis. To do that, we're going to need to know how to factor this, or it'll be easier to find the x-intercepts if we can factor the numerator and denominator. So we'll review a little bit of factoring, but we'll find the y-intercept first. So if we're on the y-axis, we know here is where x is equal to 0. The x equals 1 is a vertical line, x equals 2 is a vertical line, x equals 3 is a vertical line. The x equals 0 is a vertical line, and it happens to be the y-axis. Y equals 1 is a horizontal line, y equals 2 is a horizontal line. The one on the x-axis is y equals 0. So this is y equals 0, this is x equals 0. If I want to know where the graph crosses the x-axis, I would set y equal to 0 and solve for the corresponding x values. To find out where the graph crosses the y-axis, I set x equal to 0. And that'll give me where the function crosses the axis. So I'll evaluate this at x equals 0. So I'm just going to replace all of my x's with zeros. And you can see that we just get a sum of a bunch of zeros and a 4 in the numerator, and then the sum of a bunch of zeros and a 12 in the denominator. So in x equals 0, y equals 1/3. So that means the point x equals 0, y equals 1/3 is on our graph. Or in other words, our graph is going to cross the y-axis at 1/3 at a particular point right there. And to find the, sorry, this is a y-intercept. To find the x-intercepts, we have to factor that numerator and denominator as much as possible, cancel any common factors, and then we'll set the remaining numerator equal to 0. So we've got this. And we're looking at the numerator first. And we might ask ourselves, like, is there an easy way to factor that? And to do that, I usually, if I've got an expression with 4, or a polynomial with 4 terms, I often graph the first 2 and the second 2, and make sure you put a plus sign in between just to remind yourself that you're not multiplying them, you're actually adding them. And you say, well, can I factor this group and this group separately? This is called factoring by grouping. If you can, we do that. And then we see if there are any common factors with what's left. So we'll look at these 2 terms and we say to ourselves, do x cubed and x squared have anything in common? And they do. They both have an x squared in common. And then we say to ourselves, okay, x squared times what gives us x cubed? Just x. X squared times what will give us a negative x squared? Just a -1. And then we're going to factor something out from here as well. You've got a -4x and a 4. You say, do these have anything in common? Well, I could take out a 4, or I could take out a -4. Either one would be fine. But you know that when you're done with this, after you factor that expression out, or that term, that factor out, you want the first term of the resulting expression to have an x in it. Since this is multiplied by -4, we're going to factor out a -4. So if -4 times x gives us the -4x, and -4 times -1 gives us the 4. So I factored the first group and I factored the second group. And then I look at the results for either both of those. I say, does this expression, or do this expression and this expression have anything in common? You say, well, they both have an x minus 1. Well, you can factor that out as well. So we have x minus 1. And then we open a second set of parentheses. We say x minus 1 times what gives us the first group? It's x minus 1 times x squared. And x minus 1 times what gives us the second group, which is the -4. So you have that. And then recall from your algebra classes that we have a difference of squares. A squared minus b squared factors to a plus b times a minus b. And x squared minus 4 is the difference of squares. A is x and b is 2. So this factors to x minus 1 times x plus 2 times x minus 2. That's our numerator. And we're going to look at the denominator as well. In order to find the x-intercepts, we need to reduce this as much as possible. Typically, you would say, okay, I'm going to set y equal to 0 and solve for x. And you might be tempted to think, well, if this fraction is 0, then the numerator is 0. And that's right. But if there are any common factors in the numerator and denominator, like that point's not going to be included, or the x value that causes that factor to be 0 won't be included in the domain. So we need to make sure that we simplify that function first. So we'll look at x cubed plus 3x squared minus 16x plus 12. And we'll say to ourselves, okay, if I try factoring by grouping, does it work? If I group those two and that to get those two together, make sure you're adding those. Can I factor by grouping? We'll see. Say, do x cubed and 3x squared have anything in common? They do. They have an x squared in common. And then x squared times what gives us x cubed and x. X squared times what gives us 3x squared, just the 3. And then we look at the -16x and the 12. We say to ourselves, do they have anything in common? Well, 16 and 12 have a factor of 4 in common. But again, when we factor something out from here, we want an x as our first term, because we're hoping that we'll have an x plus 3 left when we're done. If I factor out a 4, or excuse me, a -4, I have -4 times 4x would give me the first term, and -4 times +3 would give me the second term. So I'd say, uh-oh, I don't think factoring by grouping is going to work this time. After you do that, you look at this expression and this expression, and you say, do they have anything in common? And they don't. You might be tempted to think, oh, there's an x plus 3 there, but this is actually a 4x plus 3. So that's going to be a bit of a problem. So it looks like with that choice of grouping, this expression doesn't factor by grouping. The other option is you can group the x cubed and the 16x together, and then the 3x and the 12 together. The 3x squared and the 12. 3x squared and the 12 have a factor of 3 in common. But if I factor out something from the x cubed and the -16x, I'll just factor out an x. They have an x in common. It's just not going to get us where we want to go. So factoring by grouping, excuse me, does not work for this. So we need to try something else to factor this. And one way that we can factor that expression is to use what's called possible rational roots. The possible rational roots of a polynomial function are given by the following. You take all of the factors of the constant term, and you divide by the factors of the leading coefficient. So in our case, the constant is the 12. So we want the factors of 12. And we want to divide by the factors of the leading coefficient, which is an implied 1. Factors of 12 include plus and minus 1 and plus and minus 12, because 1 times 12 is 12, of course. Then we've got plus and minus 2 and plus and minus 6, because 2 times 6 is 12. Plus and minus 3, plus and minus 4, because 3 times 4 is 12. And I'm using plus and minus because you can do 1 times 12 or negative 1 times negative 12, and so on. And then we take all of those numbers on the list and we divide by the factors of 1, which are just plus and minus 1. Dividing by 1 doesn't change anything. So we actually have a list of 1, 2, 3, 4, 5, 6, 12 possibilities. Negative 1 and 1, negative 2 and 2, negative 3 and 3, and negative 4 and 4. And you just keep going down your list. Now, these are the possible roots of this function. And we have another fact that we use. Say if f is a polynomial, and x minus or x equals k is a root, then x minus k is a factor. Remember what a root is. It's just at an x value that causes the function to be 0. So these are possibilities for the possible x values that cause that function to be 0. And that's going to help us factor, because if I know an x value that makes this function 0, then I know what the corresponding factor is. So if x equals 2 is a root, then x minus 2 would be a factor. If x equals negative 3 was a root, x plus 3 would be a factor. I'm just writing that down so that we can see a concrete example. So we're going to plug those, plug some numbers in from this list to that function. And if we get a 0 out, then it'll allow us to find at least one factor of that cubic polynomial. So we've got x cubed plus 3x squared minus 16x plus 12. And we're just going to guess. I like to guess small integers first. So I might guess, let's say x equals 1. That's going to give me a 1 plus a 3. 1 plus 3 is 4. Minus 16 is negative 12. Negative 12 plus 12 is 0. So x equals 1 does work. And I have a tendency to try that in my head first and then actually plug it in. So I have 1 cubed plus 3 times 1 squared minus 16 times 1 plus 12. And we say that equals 0. So that means x minus 1 is a factor of that polynomial. Okay, well, if x minus 1 is a factor, and this is a cubic polynomial, well, that means that that cubic polynomial can be written as one of its factors times some quadratic polynomial. So it's going to be ax squared plus bx plus c. To find that quadratic polynomial, we just have to take this polynomial and then divide by x minus 1. And there are a couple of ways we could do that. We could do that using long division, or we could use that using what's called synthetic division. I think I want to use synthetic division. So we'll say the quadratic polynomial that we're interested in is x cubed, and I forgot the rest of the polynomial, plus 3x squared minus 16x plus 12. And we're dividing by x minus 1. If we want to use synthetic division to find this quadratic polynomial, to do this division problem. We set this denominator equal to 0 and solve for x. So basically you get x equals k in every case. We already know that x equals 1 was the root. So you're going to put that in a little box over here. And then you need to list the coefficients of the polynomial in the numerator. Sometimes we call that the dividend. This is the dividend. And then in the denominator, we have what's called the divisor. And you have to do this in descending order for all powers of x. So you have a cubic polynomial here. So you need an x cubed term, an x squared term, an x term, and a constant term. If you didn't have one of those on your list, you'd have to add in a 0. So if there was no 3x squared here, if that was my polynomial and I was missing an x squared term, I'd have to add a 0x squared. But this time we've got all of the possibilities from x cubed all the way down to x to the 0. So we'll list the coefficients. There's an implied 1 there. So we've got a 1, a 3, a -16, and a 12. Bring down the 1. And then after you bring down that leading coefficient, you just multiply, put that product here, and then you add. Multiply and add. Multiply and add. And if you've done everything correctly, and this is actually a root, you should get a 0 here. The number in this last space is the remainder. And then these are the coefficients of the quotient. Since this is cubic and we divided by something linear, the degree of the polynomial decreases by 1. So we're going to have something quadratic. So this is the coefficient of x squared because it's a quadratic polynomial. So we have the original polynomial that we were interested in is equal to x minus 1 times this quadratic polynomial that's implied by this. So we're going to have a 1x squared plus 4x minus 12. Now that is just a rule or an algorithm. That is how we find these coefficients. I didn't really explain why this should work. It turns out this works because it's like a shorthand version of the long division algorithm. It allows us to basically do the same calculations, but without having to write the x squared, the x, and so on. Maybe in another video, if I do a pre-calculus video, we can describe why that actually works the way it does. But then, so we're trying to factor that denominator as much as possible. And remember that this is our original denominator. And we ask ourselves with this one, well, do I know of two numbers that give me a product of -12 and a sum of 4? Well, since the product is negative, what I'm really looking for is two factors of 12 that have a difference of 4. Factors of 12 include 1 and 12. The difference is 11. That's not going to work. 2 and 6. The difference is 4. So that should work as long as one of these is negative. If I want the sum to be +4, I need the smaller of the two numbers to be negative. So we're going to use a -2 and a 6. This is x minus 2 times x plus 6. We have an x and an x here, and those two numbers go in those spaces there. So our original denominator is equal to this, and that means f of x, the function that we're interested in, is this denominator. And where did our numerator go? That was our numerator. So we've got this. Now, before I find the x-intercepts where the graph crosses the x-axis, we want to simplify as much as possible. So after factoring, the whole point of factoring actually was to find any common factors in the numerator and denominator. So I've got an x minus 1 as a factor, those reduce. I've got x minus 2s as factors, those reduce. So this function f of x is actually equal to x plus 2 over x plus 6. But you have to remember that the x values that cause those denominators to be 0, or any factor in the denominator to be 0, cannot be in the domain of the original function. So this function f of x is exactly equal to this, except at 2 points. When x is equal to 1, this is well defined, but this is not. This function has a hole in it. And when x is equal to 2, this function is well defined, but this function has a hole in it. So f is equal to this as long as x is not equal to 1 and x is not equal to 2. And I guess x is also not allowed to be equal to -6, but that's sort of implied by the form of this final function at the end here. So now we've got this function. To find the, well, actually, let's write down what we just did. We'll say write f as a quotient. Simplify. Yes, let's say don't forget to cancel common factors. Well, not cancel common factors. Don't forget to state the restrictions on x. Because this function is continuous at those values, this function is not. All right. So now we're going to find the x-intercepts. And remember, to find the x-intercept, you set y equal to 0. So f of x and y are the same things. You're going to have 0 equals x plus 2 divided by x plus 6. You multiply both sides by x plus 6. You just get that the numerator has to be 0. Then if you solve for x, you get x equals -2. So when x is -2, y is 0. So that is our x-intercept. Go back here. That just tells us that at x equals, was that -2? Yes, -2. Y is equal to 0. So that point is on our graph. At that point and that point. All right. Now what else do we know? This function f of x is undefined when x equals -6, because the denominator is also 0 when x equals -6. But if x equals -6, the numerator is -6 plus 2, which is -4. So it's non-zero. So to find the vertical asymptotes, we do the following. And this, actually, I think I'm going to do it over here. We'll say x plus 6 equals 0. We're going to set the simplified denominator equal to 0 and solve for x. These x values, or the x values that cause these factors to be 0, represent holes in the graph or correspond to holes in the graph. But the x values that cause this denominator to be 0 after simplification correspond to vertical asymptotes. Again, because the numerator is non-zero and the denominator is 0. We'll say that that's a vertical asymptote of the function, or the graph of the function. So I go back here. Of course, that's not to scale. We know we're going to have an asymptote at 6. 6 or -6? It's -6. All right. It's on the other side. Looks like all the interesting things that are happening over here on the left. 2, 3, 4, 5, 6. X equals -2. When x or y is 0, x is 1/3. Or when x is 0, y is 1/3. So there's our x-intercept, there's our y-intercept, and there's a vertical asymptote. And for horizontal asymptotes, we need to look at the limits of the function as x goes to positive and negative infinity. Because it's a rational function, the function is going to have the same end behavior on the left and the right. So we're taking the limit of this function. Okay. My work is a little messy right now. As x goes to positive and negative infinity. Since this is already factored, we'll reduce the common factors. And remember how that works. The limit of the original function is equal to the limit of that simplified function. So these guys, or this function has the same limits as that function as x goes to positive and negative infinity. And then as x gets very, very large, x plus 2 also gets large. So if x was 1,000,000, this would just be 1,000,002. X is 1,000,000, the denominator is 1,000,006. And so I'm thinking it's basically 1,000,000 over 1,000,000. The 2 and the 6 don't matter much as x goes to infinity. So we're basically approaching 1. But to prove that, we call this an infinity over infinity indeterminate form. To prove that that's true, we want to get rid of that infinity over infinity problem. We divide by the highest power of x in the denominator. And we've done this before. So we divide by x. Make sure you divide every term in the numerator by x. Then 2 over something very large is something very small. Same thing with 6 over something very large, and we get a limit of 1. So that means the y values on the graph of this approach y equals 1 as x gets very large and positive or very large and negative. So y equals 1 is a horizontal asymptote of the graph of the function. Okay, so we did that. All right. So we talked about the related limits with the horizontal asymptotes, but we didn't talk about the related limits with the vertical asymptotes, and we didn't talk about the holes in the graph. So you might say, okay, how do I recognize the holes in the graph? We already know that we've got x equals -6 as a vertical asymptote. We know that as x approaches -6, this function is going to go to infinity because when x is equal to -6, that numerator is -4. When x is equal to -6, the denominator is 0. So we've got a non-zero number over 0. So that is going to give us a vertical asymptote or correspond to a vertical asymptote. And that means infinite limits on the left and right of -6. We just have to figure out what those limits are to the left and right of -6 to find the corresponding limits that go with that particular vertical asymptote. So let's think about that function. We're asking ourselves, well, how does the function behave to the left and right of that asymptote? With the limit, as x approaches 6 of our function. And of course, these reduce. In the numerator, as x approaches, this should be -6. As x approaches -6, our -6 plus 2 approaches 4. That's a positive number. And then with the denominator, as x approaches -6, our denominator approaches 0. But we have to think about whether these numbers are, or this number that's getting close to 0 in the denominator is tiny and positive or tiny and negative. We actually have different behavior on the left than we do from the right. So if I'm on the left of x equals -6, let's say like -6.0001, we would denote that limit this way. The little negative sign just means we're going from numbers that are slightly less than -6, which is -6.001 in this case. When we approach from the left, -6.0001 plus 6 can give us -0.0001. That's a tiny negative number because we're approaching from the left. So you have something that's approaching 4, which is a positive number. We get a positive number divided by a tiny negative number. So that means the limit is going to be -infinity. That means the function is going to approach -infinity over here on that side. And then we'll look at the same expression as x approaches -6 from the right. And I bet you can guess that this is just a test value. We're just plugging in any particular x value to the left of -6. You could have picked -6.1 if you wanted to, or -6.01. Any number that's close to -6 and on the left of -6 will work. Try not to use like -7. That might be a little too far away. So we'll have, we're now going to look at the limit as x approaches -6 from the right of x plus 6. Well, we know that that's 0. But if we're approaching from the right, the numbers might be like -5.999. So you take that number and add 6 to it. And that is a tiny positive number. So when we evaluate the limit as x approaches -6 in general of our function, and again, that reduces to x plus 2 over x plus 6. We're gonna have different behavior on the left and the right. As we approach from the right-hand side, we've got a positive number divided by a tiny positive number. And a positive number divided by a tiny positive number is a large positive number. Like 1 over 1/1,000,000 is a million. So it's just gonna get larger and larger as that denominator gets smaller and smaller. So we get infinity on that side. So as we approach -6 from the right, our graph is gonna look roughly like that. Okay, so we know that. We know our graph passes through this point. We know it passes through this point. You might say, okay, well, what about those holes in the graph that were mentioned? We talked about the vertical asymptotes and related limits, and we talked about the horizontal asymptotes and related limits. Now we're also interested in holes. The holes in the graph correspond to points where the limit is well defined, but the function itself is not. In this case, the holes in the graph correspond to these particular x values. Or if you prefer, you can use open circles or open points. That's a point that the function is going to get infinitely close to, arbitrarily close to, in the x and y direction. But we never actually get there. That point's not on the graph, it's omitted from the graph. And this function itself turns out to be continuous at those points. So we can just plug in those x values over here to get the right limit. But we can't plug in those x values over here because the original function is not well defined at those values. So since we're interested in these x values that correspond to the factors that canceled, we're going to take the limit as x approaches each of those values, which just means plugging those values into here to find out what the limit they're supposed to be. I still like to write the factored form of the function just to remind myself I'm actually taking the limit of this function. Those reduce. So the limit of that function is equal to the limit of this continuous function. And then I can plug in the 1 for that continuous function. So I get 3 divided by 7 for the limit of x approaches 1. So the limit exists, it's finite, it's 3/7. And but the function value itself is not defined. So the point xy equals 1, 3/7 is an open point on the graph. Sorry, the width. Right. And similarly, if we take the limit as x approaches 2 of the function f of x, those x minus 2's reduce as well. So the limit as x approaches 2 of f is equal to the limit of that reduced function or the simplified function. We can plug in 2 because this function is actually continuous. We end up with 4 divided by 10 or 2 bits. So the point x equals 2, yes. Y equals 2 bits is on the graph as well. Or it's an open point on the graph as well. Or we could say it's not on the graph, it's omitted from the graph. Okay. So at x equals 1, y is equal to 3/7. Very, very small. And at x equals 2, oops, y is not equal to 3/7. And x equals 2, y is equal to 2 fifths. Also small. And we know that the function is supposed to approach the line y equals 1 as x goes to positive and negative infinity. So maybe the graph looks like this. I'm not actually sure. A little rough, but we imagine that the function is going to approach x equals -6. It crosses the x-axis at x equals -2, crosses the y-axis at y equals 1/3. The function has an open circle at 1 and, what was it, 3/7, and an open circle at 2 and 4/5. So just to confirm this is true, let's write f of x or graph f of x on desmos.com and see if the graph on the graphing calculator looks like our picture. All right, so when we graph the function, this is what we get. This is what it looks like. I graphed x equals -6, that's our vertical asymptote, y equals 1. And then I graphed the 2 open points and the function itself. But I noticed when I graphed those points that it didn't look right. Notice that this one at 2 and 2 fifths, which is 0.4, doesn't quite line up with my graph. See it? Why I'm having trouble with that. Since I noticed that that doesn't look right, I'm thinking maybe I made an arithmetic mistake, or maybe I just copied the answer down incorrectly. So we'll go back to our paper. Oh, I think I was forgetting to share anyway. I'm sorry about that. Notice when I tried to graph that point, it doesn't cross the axis at the point that you'd expect it to. If we try to zoom in, see how it's below the graph? That tells me that's the wrong point. I must have made a mistake. Let's look at that one. It's actually on the graph. So that one works. This one doesn't. So I must have made a mistake. Let's go back to our paper and see what we've got. I've got I substitute x equals 2 into this function. 2 plus 2 is 4, and 2 plus, oops, that should be a 6. 2 plus 6 is 8. And then that should be 4 divided by 8, which is 1/2. That should be a 1/2 rather than a 2/5. So we should expect a 0.5 rather than a 0.4. Let's go back to the graph and see if that's consistent. And now it's on the graph. It's exactly like what we would expect. Okay, now let's zoom out. All right, it looks like our graph got the vertical asymptote x equals a -6, the horizontal asymptote at y equals 1. Notice that the function gets infinitely close to x equals 6, gets close if we want to x equals -6 as we approach from the left and right. And then the function values are approaching these two open circles as x approaches 1 and 2. As x approaches 1, we get very close to that point. As x approaches 2, we get very close to that point. I feel like we must have made another mistake as well. Notice that the limit as x approaches -6 from the left is positive infinity. And as the limit as x approaches -6 from the right is negative infinity. I think I may have made a calculation error there as well. Let's go back to our paper. Let's say, okay, this graph suggests that it was supposed to be the other way around, right? So they have it going this way and then this way. The graph on Desmos looks more like this. That's supposed to be the y-axis, sorry. X equals 0. That's what Desmos looks like, and I had this. So that tells me that my limits from the left and right must have been inaccurate when I did my calculation. So let's look at these limits as x approaches -6 from the left and the right. Oh, I see what I did wrong. Do you guys see it? X is approaching -6. -6 plus 2 is -4. This is a negative number rather than a positive number. So here, as we're approaching x equals -6 from the left, I get a tiny negative number as that denominator approaches 0. It's approaching 0 from sort of the negative side. So we have a negative divided by a negative. I didn't write that down here. The negative divided by a negative should give us a positive infinity as we approach -6 from the left. It's going to go this way to positive infinity rather than to negative infinity. Over on this one, as x approaches -6 from the right, we still get a 0 there. But if we're approaching from the right, we get a tiny positive number. The numerator is a negative number now. So we have a negative divided by a tiny positive, which is going to give us a negative. So that limit is negative infinity, which means our graph should approach negative infinity rather than positive infinity. That makes sense, since I made that little arithmetic error, that sign error is a huge difference. And we have different behavior on the left and the right. Instead of negative infinity, positive infinity, we have positive infinity and negative infinity respectively. All right, so let's look at the graph again. All right, so now everything is consistent. If the limit as x approaches -6 from the left and the right, it's infinity and then negative infinity respectively. The limits as x approaches 1 and 2 are 3/7 and 1/2 respectively, and we see that that's consistent with our graph. And then if we look at this graph as x goes to positive infinity, we're looking at how the function behaves. Well, the function is getting very, very close to that horizontal line, which is y equals 1. And as x goes to negative infinity, so x gets very, very large and negative, the function is getting very close to the horizontal line, y equals 1 as well. So that is the right graph, the correct graph. And let's write this in its factored form as well. So with x minus 2, just want to confirm that it's the same function. Let's graph x minus 1 times x minus 2 times x plus 2. We divide all of that by x minus 1 times x minus 2 times x plus 6. And it is the same function. Now, if we cancel those common factors, well, we see that the graph is the same, right? If we cancel the common factors, what we get is a function that is continuous, that has the same behavior as f of x everywhere except for x equals 1 and x equals 2. But I do want you to notice that even when I include those factors that are equal to 0 in the numerator and denominator, Desmos.com has a tendency to graph this without omitting those 2 points, the points x equals 1 and the corresponding limit, x equals 2 and the corresponding limit, even when the function is undefined there. You have to be careful. The graphing calculator may give you a misleading picture. You might look at this picture and say there's only one discontinuity, and it's the discontinuity at x equals -6. You might miss the fact that there are discontinuities at x equals 1 and x equals 2 if you don't factor and reduce. The calculator might give you a misleading answer, because when you look at this orange graph, it looks like it's continuous at 1 and 2 when it's actually not. I hope that helps. Let me know if you have any questions.